So if you are in my class and watching my videos, this is going to be a lesson 11, chapter 11, lesson 5 and 6 together in one video. There's a lot of information in these two sections that I expect are background knowledge. So we're going to expect you to know them and kind of get through two sections in one day. So first we have a warm-up. Name the polygon by the number of sides. Well, a polygon that has 6 sides is a hexagon. One that has 10 sides is a decagon. 5 sides is a pentagon. And what is a regular polygon? Of course, you remember it's a polygon with all congruent sides and all congruent angles. What is the length of the diagonal of a square with a side length of 6? So you might know this right off your top of your head, you might not. But basically, if it's 6 and 6 on each side of the square, when we create a diagonal, we create two 45, 45, 90-degree triangles. So this diagonal is 6 radical 2. In this lesson, we're going to get into some three-dimensional objects. A polyhedra is a solid that is bounded by polygons called faces and enclosed a single region of space. An edge of a polyhedra is the line segment formed by the intersection of the two faces. We tend to think of faces as sides. And a vertex of a polyhedron is a point where 3 or more edges meet. The plural of polyhedron is polyhedra or polyhedrons. So you'll notice here are two types of solids that are polyhedras. Here are ones that are not because they have circles in their dimensions. And when we classify solids, this is a little small down here, see if I can make this a little bit larger so you can see that a little bit better. But of the 5 solids above, the prism and the pyramid are polyhedra. To name a prism or a pyramid, you use the shape of its base. So a pentagonal prism is a prism that has 2 pentagons as its base. And then a triangular pyramid has a base of the pyramid is a triangle. So for instance, a pentagonal pyramid would have 1 pentagon at the base and triangular sides. We're going to identify whether these are polyhedra or not. If it is, name the polyhedra, find the number of faces, vertices, and edges. So in A, this is a rectangular prism. It has 1, 2, 3, 4, 5, 6 faces. As far as edges, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. And for vertices, 1, 2, 3, 4, 5, 6, 7, 8. For this, that's a hexagon at the bottom, so that's a hexagonal hexagonal pyramid. It has a hexagonal base and 6 triangular sides for a total of 7 faces. As far as edges, it has 6 edges along the hexagonal base, 7, 8, 9, 10, 11, 12 edges. And as far as vertices, it has the 6 at the base and 1 at top, the pointy top. Letter C, this is not a polyhedra because it has a circular base. Here are your solutions. We've gone through and counted those. And now we're going to tell whether the solid is a polyhedra. If it is, name the polyhedra and find the number of faces. So these are all congruent. So this is a square pyramid, and it has 1, 2, 3, 4 edges at the edges of each side of the base. 1, 2, 3, 4 edges connecting the 4 faces that will go up to the 1 point on top. And 4 vertices at the bottom, 1 at the top. And you can see that answer. Now that this is not a polyhedra, so it is because it has a curved surface. And this is a triangular prism because it has 2 triangles at either side. 1, 2, 3, 4, 5, 6, 7, 8 9 edges, 1, 2, 3, 4, 5, 6 vertices. So now we're going to talk about Euler's theorem. You might have noticed in example 1 that the sum of the number and faces of the vertices of the polyhedra is 2 more than the number of edges. This suggests the following theorem, and it was proved by Swiss mathematician Leonhard Euler, who lived from 1707 to 1783. So his theorem was that the number of faces, vertices, and edges of a polyhedra are related by the formula F plus V equals E plus 2. So if you take the number of faces and you add the number of vertices, you're going to equal 2 more than the number of edges. And you can use this when you're counting faces, edges, and vertices to make sure you have numbers that work. So we're going to use the number of faces, edges, and vertices to see if this works. So the number of the faces plus the vertices should equal the number of edges plus 2. So the faces on this, 1, 2, so there's 2 that are that shaped, 3, 4, 5. There are 3 rectangles. There's total there. 2 of those. And there's 1, 2 slanted rectangles for the roof. So 2 plus 3 is 5, 6, 7 faces, vertices. 1, 2, there'd be 1 back there, 3, 4, 5, 6, 7, 8, 9, 10. That should mean that this is 7 plus 10 is 15. So there is 7 plus 10 is 17, excuse me. So there should be 15 edges. 1, 2, 3, 4, 5. Maybe 1 along the back there. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I believe that I have counted them all. Let's see if we're right. It's part of the solution, and there's the rest of it. So the house has 15 edges. We're also going to talk about regular polyhedra. A polyhedra is regular if all of its faces are congruent regular polygons. A polyhedron is convex if any 2 points on its surface can be connected by a segment that lies entirely inside or on the polyhedra. If this segment goes outside the polyhedra, then the polyhedra is non-convex or concave. So as we talked about in class, it almost looks like it's tipped inwards. This is a regular convex polygon, and you can see all of these edges are marked congruent. This one is non-regular and it's concave. There are 5 regular polyhedra called Platonic solids after the Greek philosopher Plato. The 5 Platonic solids are shown: a regular tetrahedron with 4 faces, a cube with 6 faces, a regular octahedron with 8 faces, a regular dodecahedron with 12 faces, and a regular icosahedron with 20 faces. These are ones that you should be familiar with the names of. There are only 5 regular polyhedra because the sum of the measures of the angles that meet at a vertex of a convex polygon must be less than 360. That means the only possible combinations of regular polyhedrons at a vertex that will form a polyhedron are 3, 4, or 5 triangles, 3 squares, and 3 pentagons. So now we're going to use Euler's theorem with Platonic solids. Find the number of faces, vertices, and edges of the regular octahedron. Check your answer using Euler's theorem. So if we count on the diagram, the octahedron has 8 faces, hence octa, 6 vertices, and 12 edges. If we use Euler's theorem and plug those numbers in, we see that his theorem shows that this solution is correct. The other thing that we need to be able to look at or visualize is describing cross sections. A cross section is a two-dimensional plane intersecting the polyhedra. In this case, we have a cube. I can do a cross section horizontal, and on a cube I will get a square, but if I do a cross section at an angle diagonally, I'm going to get a cross section of a rectangle inside this cube. And I can also hit a cross section this way and actually get a trapezoid through the cube. Find the number of faces, vertices, and edges of the regular dodecahedron from example 3. Check your answer using Euler's theorem. So I took this picture here, brought over this image so that I can see, obviously, a dodecahedron is going to have 12 faces. Faces plus the vertices should equal the edges plus 2. So for vertices, 1, 2, 3, 4, 5. There would be 5 on the other side also for a total of 10. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 where the two fit together. So that's 32. So edges plus 2. So there should be 30 edges. Let's see how we did here. Okay. So if we work this out, there would be 30 edges. We found the number of faces and the vertices. I didn't start counting all the edges because I used the formula. For the next guided practice, describe the shape formed at the intersection of the plane and the solid. If you can see that there, but that is a triangle. And here the cross section is a circle. On this one, the cross section is a hexagon. And now the daily homework quiz. This is not a polyhedra, it's a sphere because it has curved edges. This is a polyhedra. That looks like it could be a square, but since they don't tell me that everything's congruent, I'm going to go with a rectangular pyramid. On this one, there are pentagons at both sides, so it's a prism, a pentagonal prism. Find the number of faces, vertices, and edges of each polyhedra in exercises 2 and 3. You can go back and count those. Check on the pyramid. There's 5 faces, 5 vertices, and 8 edges. On the prism, there's 7 faces, 10 vertices, and 15 edges. A plane intersects a cone but does not intersect the base of the cone. Describe the possible cross sections. It could be a point if it goes through just the very top. It could be a circle if it cuts any point parallel to the base, or it could be an ellipse if it cuts through, let's say, at an angle. You would have an ellipse formed in there. As I said at the beginning of this video, in our class we're going to do 2 lessons together because the only thing really new to you in that last lesson would have been Euler's theorem, and also maybe a little bit about the cross sections. In this lesson, we should know how to find volume of prisms and cylinders. In some cases, though, we may have to use trigonometry to find a missing length or missing height, and that's going to... So find the area of each polygon or circle. So for a trapezoid, the formula is 1/2 of the sum of base 1 plus base 2 times the height. So base 1 is 12, plus base 2 is 18, 30 divided by 2 is 15, times 3 is going to be 45. And a circle that has a diameter of 8.2 Half of the diameter is the radius, that's 4.1 squared. Remember the formula is pi r squared, so times 3.14 is going to be roughly 52.8 inches squared. We have not yet learned how to find the area of a regular hexagon. We're going to come back to that. That's at lessons at the beginning of the chapter, and we're doing this chapter in a little bit out of order, so we will come back to this problem in a few days. So the volume of a solid is the number of cubic units contained in its interior, and it's measured in cubic units such as cubic centimeters, centimeters to the third power. The volume of a cube is the cube of the length of its side. So if we have one side, since it's a cube, all three dimensions are going to be the same, so volume equals side to the third power. If two polyhedra are congruent, then they have the same volume. And the volume of a solid is the sum of the volumes of all of its non-overlapping parts. That's where we get into composite volume. You've done that in prior grades, and we'll be dealing with that in this class as well. So we're going to do composite shapes a little bit later in the lesson. I would expect you to be able to break this shape into 3 rectangular prisms and find the volume of that. The answer in this case is actually 20. We'll do this a little bit later in the lesson. I want to go back over, I'm sure you talked about this before, but for the volume of any prism, whether it's a rectangular prism, even though they give you volume of a cylinder separately, volume of a hexagonal prism, a pentagonal prism, a triangular prism, it's always the volume equals capital B, which means the area of the base multiplied by the height. So in a rectangular prism, any of the rectangular sides can be the base. You find the area of one rectangle, multiply it by the height of a prism. To find the volume of a cylinder, you're finding the area of the base, which is a circle, pi r squared, and multiplying it by the height. So for instance, to find the volume of a right trapezoidal prism, you're finding the area of the base, 6 plus 14 times 3 times a half. That's the same as 1/2. We've done it as 6 plus 14 height, which is 3. And you would get 150 centimeters cubed. Of a cylinder, the base, the area of the base is pi r squared. So 9 squared is 81. 81 times pi. 81 times pi times 6. They're doing this in a different order. Instead of doing 81 times 3.14, they're doing 81 times 6 times 3.14. If you are, try this again, 81 times 6 equals that number times 3.14. Okay, the issue here is the book is using a pi button. We're going to be using 3.14 as pi, so we're going to have a little bit of rounding difference. If they tell you to leave the answer in terms of pi, that means you don't multiply and you just have 486 pi. That would be the answer if they said in terms of pi. We can also use this formula to work problems backwards. So for instance, to find the volume, we have the volume of the cube is 90 cubic inches. They want us to find the value of x. So if the volume equals x to the third, 90 cube root in a calculator is 4.48 inches. We can solve the problem. Now we're getting into some guided practice. So as I said before, I didn't really talk about this. I would expect you to be able to break this into 2 composite shapes. This is a cubic, sorry, not a cubic. This is a rectangular prism, and this is a rectangular prism. This rectangular prism has a base of 1 squared unit, 1 times 1 times 3. So this part has a volume of 3 units cubed. This, if we broke this, this was 3 units, so now this is 2 units. So I'm going to use this as my base. It really doesn't matter which rectangular side you use. 1 times 2 is 2. 2 times 2 is 4 units cubed. So the answer should be 7 cubic units. Find the volume of a square prism that has a base edge length of 5 feet and a height of 12. So since it has a base edge length of 5 and it's a square, that's 5 by 5 is 25. And then it's 12. It's a very bad drawing. It's a very bad drawing. But you get the point, it's 12 feet high. So 25 times 12 is 300. It has a volume of 300 feet cubed. And the volume of a right cylinder, here we don't have to worry about that pi button. The volume is 684 pi cubic inches. Remember, we're going to find the area of the circular base, which is pi r squared times the height. So if I divide both sides by pi, I get 684 equals r squared. They told me the height is 18. So I take 684 and divide both sides here by 18. I get 38 equals radius squared. So the radius is the square root of 38. And that is going to be, I wrote 36, but I should have written 38. 38 divided by 2, if I'm just checking my simplest radical form, is 19. So it should be radical 38. In the last section, 11.5, we had Euler's theorem. Here we have Cavalari's principle. Consider the solids below. All three actually have equal heights and cross-sectional area bases of B. Mathematician Bonaventura Cavalieri claimed that all three of the solids have the same volume, and the principle is stated below. If two solids have the same height and the same cross-sectional area at every level, then they have the same volume. This comes from, remember, all of the formulas are actually the area of the base times the height. So if all of the cross sections are the same, that means the area of the bases are the same, whether it's a square, parallelogram there, or an oval. So they all are going to have the same volume. Now this will be the first time you deal with an oblique three-dimensional object. So an oblique cylinder, a right cylinder, which we've always dealt with, basically the center of the base and the center of the base would form a line that would be perpendicular with the base. In this case, it's tipped, but Cavalari's principle allows you to use the same theorems we've been using, the same formulas to find the volume of the oblique cylinder. We can still find the radius is 4, so the radius squared, 4 times 4 is 16, times 7 is going to be 112 pi. And if we wanted to use a calculator, we could then calculate that out to 351.86. If we use our calculator, we're going to get a slightly different number because of rounding using 3.14. Your EOC will tell you whether to use pi button on a calculator or to use 3.14 on a calculator. The planter is made up of 13 beams in centimeters. Suppose the dimensions of each beam are 30 by 30 by 90. Find its volume. So each of these are 30 by 30 by 90. So the area of the base B can be found by subtracting the area of the small rectangles from the area of the large rectangles. So you'll see, remember here, this is 90, this is 510, the whole thing, by 90. That's the area of the large circle. and then this large rectangle, excuse me, and then there are 4 smaller rectangles. And the 4 smaller rectangles are 30 by 90. So we find the area of the large rectangles, 90 times 510, which is what they've done there, but they don't show you that number, is 45,900. And then we've 4 of these smaller rectangles that we're taking out. 30 times 90 is 2,700 times 4. And if we take 45,900 and we subtract 10,800, we get 35,100. Okay? And then the formula for the volume of the prism, of the total, if each one is 35,100 times 30 of them, we get the volume of the planter is 1,053,000 centimeters. So they want us to find the volume of the oblique prism shown below. So each of these, this is 9 times 5, which is 45, divided by 2. So the area of the triangular base is 22.5. Times 8 tall is 180 meters cubed. For this problem here, they want to find the volume of the solid shown. This is a triangular prism that is sitting, actually not on its triangular base. I'm going to have to find the volume of this triangular prism by finding the area of this triangular base and multiplying it by the height. So I'm looking at this first. And this is an equilateral triangle. That's 10. When I divide it in 2, this is 5, and this is 5. This makes 2 30, 60, 90 degree triangles. So this here is going to be 5 radical 3. So 5 radical 3 times the base of 10 is 50 radical 3. And 50 radical 3 divided by 2 is 25 radical 3, which is approximately square root of 3 square root, oops, I did something wrong here, 3 square root, I did it right, times 25. 43.30 is the area of this base. I'm going to multiply that by 6, and I'm going to get the volume of this triangular prism is about 259.8. But I need to subtract out this prism inside. So this base, I don't know if you can even see it anymore, has a square bottom. These were all congruent. See this better? All those congruent marks, 3 by 3 by 3 by 3 along the bottom perimeter. So 3 times 3 is 9, times 6 is 54. So this rectangular prism has a volume of 54. So 259.8 minus 54 is about 205.8. And they rounded to the nearest 205.81. And on to the daily home quiz. For number 1, we can't do that yet. We're going to come back to these. We have not learned yet how to find the volume of a pentagon. But if we want to find the volume of a right triangular prism with height of 32 inches and base height 12 inches and base length of 18, 12 times 18 is 216 divided by 2. So that's the area of the base times 32. And we get 3,456 inches cubed. Find the volume of a right cylinder with height of 30 and a diameter of 14. If the diameter is 14, the radius is 7. 7 squared is 49. times 3.14 times the height of 30. Now our answer is going to vary slightly because we are not using a pi button. We are actually using 3.14. We can also find, next problem is a word problem. A cylinder beaker with a diameter of 10 inches and a height of 12 inches is filled with water, and then it is poured into a rectangular pan that is 14 inches by 9 inches by 3 inches. What is the volume of each solid? Would the water overflow the pan? If so, what is the height of the water in the beaker after the pan is filled? So this problem is quite a bit of different steps. I really like it. So let's look at what we have here. So if we have a cylindrical beaker, so the volume of the cylinder is area of the base. They gave us a diameter. So the radius is 5. 5 squared is 25 times 3.14. That's going to be the area of the base times the height of the cylinder, 12, gives us 942. For the pan, the volume of the pan is 14 times 9 times 3 is 378. So, is the volume going to overflow it? Yes, there's more in the cylinder than in the pan. And there's more by 564 cubic inches. If so, what is the height of water in the beaker after the pan is filled? So we want to know when the volume is 564 and we had pi radius squared height, we want to know what the height is going to be. So if you remember, our radius was 5, 25 times 3.14 is 78.5. So the volume, the area of the base is 78.5. When I take 564 and I divide by 78.5, I get almost 7.2. So the height of the water, when I pour some out to the cylinder, is still going to be about 7.2 inches high. And we have the correct numbers there. So here there is homework for tonight from lesson 11.5 and 11.6. I know we've done a lot, but I think you can handle a lot. And enjoy.